And welcome. Okay, so this is the third webinar of the Builder Crash Course. So we're in a fifth day of the build here. We're moving right along. We're building a house in 14 days, which is pretty cool. 720 square feet. Now let's go right to the meeting. I'm going to present. So I'm going to share my screen first. Share screen, entire screen. Share. View and slideshow. Okay, so remote people, can you guys see that? Can you guys see it? Okay. So let's talk about an exciting topic, from cordless drills to printed cities. Cities, wow, okay. 3D printer construction set. So what's real? For us, 3D printing is extremely interesting because 3D printing itself gets us about $20,000 reduction from 60 to 40. Okay, in materials for about a 1,400 square foot home. Okay, very nice. Combined with other savings like there's lumber, concrete, steel. That's other technologies and machines. But that we're down to 20K if we have all those technologies. We don't have that right now. Okay, so it's about development. We're working on it. But let's look at the potential of just for a reality check. Like, you might think in a house, what's plastic? Like, what do we got here? But let's go through some of those, what some of those things are. Okay, so we're going back onto the wiki. So on one side there's machines and materials cost reduction. So you can see this. I'll send the link tomorrow once again, just like normal. $3,900, $640 based on the exact costs, build costs from CD Eco Home 4, which is for sale right now in Maysville, Missouri for $239,000. So we spent $43.40 on construction machines. In other words, if we had our own machines, I mean, you got to do skid steers, trenchers, backhoes, all kinds of stuff, multiple times because there's different phases. Yeah. And then you got materials cost reduction, which we're totaling to $35,300. Wow. Okay, let's look at materials cost. And once again, write down all your questions right now. Get your notebook. According to yesterday's theory seminar on rapid learning, I'm not seeing any notebooks here.
Digital notebooks.
But you can also have a digital notebook if that works for you. But you can't really carry that around when you're swinging a hammer. But
don't tell me what I can do, buddy.
Okay, let's look at some details here. So let's focus. I'm not going to go into the wood and other things. Let's talk about wood and plastic, lumber composites and components, plain plastic, wood plastic composites, 25.9K, which is doable. I mean, I would actually say, depending what scenario you're looking at. If you're talking about commercial production where you've got parts that are code approved and certified, no, there's a low-hanging fruit section, which is like 12,000 that we can do right now within existing codes, within technology that we have already. The 25.9K would then go into once we get things certified or developed better. Like, for example, to give you an example, a window. Okay, you got panes of glass. The typical vinyl window is a plastic frame made of vinyl. You've got gaskets and seals, but it's essentially a bunch of plastic and some glass. It's quite expensive, like around $200, $300 for a window. But if you get yourself a pane and 3D print the frame, you effectively have it, because you can actually do things like print rubber gaskets and things like that. And then you can actually go into sucking the air out or filling with argon and making an airtight seal to do that. But now that would be more like, here's quality control and a developed technique where you can actually do it. But in principle, is doable. But let's start with the stuff that's easy, like $12,000 worth. Okay, like there's a lot of blocking in the house, right? You can be 3D printing that. Like, say all the blocking in some of the modules that is non-structural, that if we sent it to the building department, like, they would ignore that because that's not part of the structure. It would actually pass codes. There's actually $3,000 of non-structural infill because of excess framing. Like, we have modules that are 24 on center, but we double up the stud every 4 feet. Well, we could actually use one of those as 3D printed non-structural because the structure already allows us the 24-ounce center by itself, when we double it, you can literally take one of those out and replace it with something that's so-called not code. Not that it won't perform, like it can still perform, but the codes wouldn't recognize that that's plastic lumber, that's not approved. They would can you, but they wouldn't, because we already have that stud next to it. So you could save actually $3,000 in excess framing that we already use, and which is more about, like, if you want to build for expansion and have extra strength that you don't really need, that's there. If you were to go to multiple stories, I mean, you might not be able to eliminate that. Okay, interior wall modules. There's $1,000 in lumber out of those, and I'm actually basing this off the Cidico Home 4, the 1,400 square foot, the 2-story version. 1,000 in lumber for interior wall modules. That's the fact. That could be 3D printed because it's not structural or load bearing. That would actually pass codes. Trim's actually a big one. $3,265. And what is that? Like trim, like around windows. Okay, you can look at the details. But what is trim? Like, for example, PVC trim, like for example the white window surrounds on the Cidico Home 4, that's expensive trim actually, and you can 3D print all that kind of stuff, but you can displace 3,000. And this is like aesthetic stuff, but this is standard if you're selling a house.
Yeah,
if you're building your own house, I mean, maybe you skimp out on that or whatever. I spent $472 on GeoGrid. That's the thing that stabilizes the gravel driveway for pervious pavement. I spent $250 in geotextile, which is 3D printed. That's PET plastic. You can literally print that in flat sheets. PV mounting. Those are just simple blocks that are with basic cutouts with particular geometry to hold the PV panels. It's $500 in that, in terms of all that lumber there. There's a sewer tap, $100. $500 I spent in landscape block. That could actually, you can do plastic lumber or plastic decks. Like for example, if we did a driveway with pervious pavement, instead of using block, you could use plastic block, like they have plastic lumber for decking. And I'm noticing I didn't include the deck right now. The deck could be plastic lumber. It's not like any critical structural element. You can print your deck and stuff like that. Okay.
How does that react for the weather?
Say questions.
Oh, sorry,
Questions?
sorry.
Yeah, let's do questions for.
Yep,
Write that
I'll write
down.
it down.
So let's look at more. What else can you print? Well, obviously plumbing, right? And if we were like the plumber, the plumbing inspector is going to check that and say that, oh, that's not certified national NSF, whatever that is, national NSF certified. That's the company that certifies plumbing components. You don't have a label from a manufacturer. Like, you wouldn't be able to do that necessarily that easily, unless you have no codes like we don't have here, where you can 3D print your plumbing and you're perfectly fine because the guy doesn't check it. And you can make it happen. I mean, I'm not saying that this is like trivial. Like, you have to develop the proper quality controls and techniques, smoothness and all that, replicability, starting with machines that all function the same and all of that. So if you talk about distributed quality control on that, you'd have to degenerate your manufacturing infrastructure. Like, how would this work if you actually try to scale this, right? You'd have to have identical printers running identical code, running identical materials, and so forth. But we can document all of that. Like, we can do that to a very large extent. So for example, if now we get a collaborating engineer to, now they might, like for the first house that's 3D printed plumbing, they might have to certify that because it's non-standard parts. So who would that be? I don't even know what kind of an engineer they would call out for that, but probably a civil engineer would be invoked to stamp this. This is actually legit. You're not going to pollute and die of your own waste in your house. But once we certify one system, if we have a complete design that we open source and publish, that gets us to the fact that the next guy can do it much more easily, or they can hire our engineer to basically rubber stamp it because they're intimately familiar with it, as long as we're making the same copy. We're not modifying that. And with the designs that we're developing to a high level of development, we do that. We have, like, the design for example, we're getting the photovoltaic system, hybrid inverter system, certified by an electrical engineer from the Maysville house. And because we're going to build the exact same one in St. Joseph, that will likely pass codes there. And if not, we will get our guy to actually stamp it. But that will be trivial because he's done that design. So if he's a collaborator, he wouldn't charge us a lot, and he might even do it for free. So because we already paid him, we'll pay him. We'll pay him good money to do good work and open source the design. He gets paid, and he gets the benefit of reducing house costs for a lot of people. So now you don't have to spend, like if you have to get that engineer, you're paying $1,000, $2,000, $4,000. We paid $4,000 to get the structural engineering for this house because we used some non-traditional components, like the wall modules. We were actually concerned that they're not code approved because people just build walls their standard way, right? So we got this actually engineered and stuff like that for the details that we were doing. It cost us $4,000 for nothing, for stuff that they look up on tables and just put a bunch of. We basically took our CAD, put it into nice engineering paper drawings, and just copied and pasted standard language from other places, from existing code books, and said this is good. So they didn't do any work. They don't do actually any calculations. It turned out to be completely reference design. Okay, but anyway, getting off
So he still
track.
charged you $4,000, right?
And charged me $4,000. So if you have innovative design on anything that the system has not caught up with, you're talking about thousands of dollars of legal fees, compliance fees that you have to count in. And with our open source methods here, we try to eliminate all of that. Okay, so plumbing, like electrical conduit and electrical boxes, all kinds of stuff, boxes, mounts, other fittings. There's just a ton of plastic in the electrical part. Heavier research needed. Interior insulation, for example. Well, vinyl siding, windows. We paid $4,000 in windows for the house. $3,000 in doors, but once again, those are things that, like $1,000 in roofing and stuff, the membrane that we use. So there's like $13K right there for other things. So that's real. Those are real numbers, and certainly not trivial. And therefore, the question comes to how do you actually do this in practice? And I would say it costs $1 million to develop this and $30K to replicate. What am I saying here? So to develop all the techniques, printers, shredders, filament makers that are production grade, you're talking about maybe a year of time with maybe 10 dedicated engineers, or maybe. So I kind of go through this R&D investment. Right now we could get an off-the-shelf shredder from China or America, like 20K. We can get an off-the-shelf filament maker for like 10, 20, 30K from China. Like here they would be probably more expensive, like probably in more like the 100K range. Make printers that we have done already. Large format printers, 4,000 each. We can also skimp out smaller size that are about 1 square foot print bed, high quality with heated chambers. It would cost us, heated print chamber, it would cost us around $2,000. Right now the bill of materials for our 3D printer that could do up to a 12-inch bed is around $500, $700, maybe something like that. We add a few more developments such as a heated chamber where you can print any plastic, including things like polyethylene, which you can't print on a regular printer because it just warps like crazy if you have an open chamber and stuff like that. So okay, 24K in 3D printers, let's say we get down to the one square foot printer. Then you also have to think about, well, 1 square foot doesn't get you a lot, right? How do you get all these things? There are also conveyor belt printers, which are, there's various options, but one that I saw in Europe that was actually looked like it was production grade. So if you Google belt 3D printer professional grade, what do you get? They get pretty expensive. You can get cheap ones like on AliExpress, but what's this about? It prints at an angle and it prints infinitely long things, and it's just like a square footprint device. So you can print a pipe that's 12 inches across, infinite length. It just keeps printing on a belt. Now you'd have to have a little conveyor that receives it. I mean, I don't know, like, is this thing even available? It says whatever it showed. I mean, do you trust this? Maybe you get one that works. Now they're not. I was looking at this just a few months ago, and all of them were like out of stock. Like, let's look at black belt. So I mean, this is what do you get? Are these available and in stock? Yeah, actually, and these are not cheap. This one, yeah, this is actually the one I was looking at. It's like $5,000 for, but this does look like pretty much professional grade, so you can print a lot of cool stuff. So there's possibilities with even small scale printers. You can do a lot of cool stuff. And it's okay. So regarding that, 4 engineers and 4 builders, 1 year, like 800K. Like if we have a team of about 10 people for a year, full time, like all out engineering and development and testing and prototyping and testing again until you work all the kinks out. It's probably like, if you hired the people, it would be like $1 million. Or you can try to coordinate that through open source channels. That's a pretty hard thing to do. We're still trying to do that. We're trying to find methods where we coordinate large scale build events where we invite. We would actually, the way it would look is, you invite the public. Yes, there might be a little fee, so you're if you're paying attention, because if you don't pay, a lot of times people just don't take it seriously. But then spend money on hiring a dozen or so, or at least a few dedicated subject matter experts that know about this stuff and can do it in their sleep, right? Like for example, if we're building a 3D printer with a heated chamber, we'd get somebody who's built heated chamber 3D printers. There's a little block there. Nobody knows how to do that. They're all proprietary. I mean, it's super hard to find any people that actually know what they're doing. And if you find somebody, they're like, no, sorry, I work for Stratasys. I can't do that. That would violate my non-disclosure agreement. So you can't get it. You kind of have to develop it yourself. But if we do it, like just get standard engineers who are repeating, who once again reinventing the wheel, which is what we're doing. I mean, because you'll get a lot out of open source content or patents or this or that, but that does not substitute for the work that like we did, for example, in CD Home 4, where everything is absolutely documented and perfected. Okay, you're not going to get that, and that takes a lot of work. It's the territory where you don't just get hippies off the street and just random contributors. This is super focused, dedicated development that very few people know how to do, have the discipline to do. So I'm saying, like, let's spend $1 million on it. Or however, if we can do it more efficiently, that would be great. But once you can replicate, okay, so say you develop this, we can build this stuff for dirt cheap. Like for a shredder, how about we take the existing skid steer auger, which has got more torque than you'd ever wanted. It's good enough to drive piles into the ground. I can run a shredder. So for a shredder, you're talking about a box with the shredder blades and some gears in there that, or not even geared, just gearless, because you already got the gears in a infrastructure, for example, from a skid steer auger. So it'll cost you like $2,000 for like commercial grade where you're shredding tons per day, right? So you got industrial productivity on a small scale. Filament makers, we've built those. We built one that makes 1 kilogram of filament every 2 hours. If we just lived with that, and this is where the future development in this requires us to say, let's take that to a commercial product release, or take any of the existing ones. I'm not aware of any open source version right now that works. There's some small ones that are not really production grade, and I haven't really searched that in detail lately, but about a year ago there was nothing that I saw that was open source production grade filament makers, including the one we built. It worked for us. We got a spool of filament. But then it broke. You got to have the reliability engineering on it and all that, just a robust system. So that means once the development that we put into this. But if we even use something like that, if we get it to work, so that means we know the cost structure of it. It was only like $600 cost for something for a kilogram per hour production, like 24 kilograms a day. You can just leave this thing running all day, right? That's not bad. Well. If you want to build a whole house, like literally structural lumber that you might have plastic filled with wood, like wood-filled plastic for various things. If you're talking about serious grade production of materials, say you even do a hybrid CB or straw bale where the plastic is just infill altogether, well, you still need quite a bit of plastic if you're going to take care of all the different structures that you can do with printing, and you need a few tons of, like 1 ton per week to do a house build every 8 weeks. If we're assuming like you're literally like 3D printed plastic house, which would be some kind of a durable plastic mixed with, for example, wood dust, which actually would look and kind of feel and smell like wood actually. So you can do that kind of stuff, which is interesting because then you're taking recycled plastic and turning it into build material. But that level of filament making would cost us about $4,000. But in any case, if you're going to get yourself a bunch of 3D printers, so I'm talking about 12 four-headed printers. 4 heads. They make 4 of the same object at the same time. Why? Well, because printing rate is quite limited. Like using open source printing heads, you can get up to easily. You can get to about 5 pounds a day. So if you got a 4-headed printer, you got 20 pounds a day. If you got 12 of them, you got 500 pounds a day. That's getting into some serious production ability. They're just running by themselves. You're not babying them, but they have to be reliable enough to the point that you're running them for days and making parts. So once we invest in this, for $30K, you can start a business making houses that have a lot, or running this business of making CDeco homes that are not $60K in materials, but $40K and so forth. So because the printing filament costs are negligible, if you go from scrap, you can get. So concrete 3D print. So let's talk about other materials. Concrete. It can save you so much. You can build 4%. We discussed that number the other day. So walls are only 20%, and the house build cost in materials is only 20% of an entire house. There's land. There's investors that are taking their cut. There's other costs. There's legal costs. So anyway, great. But if you actually are building your own house, when you build yourself, get it? When you build yourself, you're actually saving 20%. That's good. So Chinese companies print 10 houses a day. Yeah, great. Save yourself 4%, and they probably pocket the change. So how about, okay, let's talk about real stuff we want to do. Rubber tracks or punctureless tires for the skid steer, which costs like $300. The regular pneumatic tires cost $300. You got to replace them every year if you're doing aggressive work. I mean, ours, I see some major slits in them already. We're only headed for like a month. But rubber, like those tires that are airless, they cost like $800 a pop. They're not cheap. And they weigh about 600 pounds. So they're charging you about $1 a pound for their tires, a little over $1 a pound. Okay, so what happens when you go, like, let's take these tracks here. Okay, these tracks, I looked at their weight. They're about 600 pounds each.
$4,800 for a pair, 7 feet.
Yeah, these are like industrial grade skid steer tracks. Okay, so how about saving that every 2 years?
But the skid steer only lasts 4 or 5 years anyway, right?
Yeah, but part of that is that, okay, so you're going to go through a couple of tracks like this. The replacement there is like 2 or 3 years. I looked at the warranty on that. They warranty this for 1 year. Great. That means they're going to break after, whenever after that. So, okay, but let's take a look at rubber punctureless tires that are $800 a pop. They only weigh about, you can get them down to about 300 pounds of plastic, probably even 200 for solid ones that are still industrial grade. Okay, if you got it, say, conservatively 300 pounds, well, what's the cost of plastic from the waste stream? Well, you can get ton bales of plastic for about $20 or $50. So it gets down to more like a few cents per pound in terms of your cost. You can look at plastictrader.com or whatever, like there's recycling traders online. I found thermoplastic urethane, so that's the printable rubber, TPU it's called. You can get that for as little as 13 cents a pound. Okay, so what's that mean here? 300 pounds times 13 cents. What is that, $40 in rubber?
Less than
And electricity costs are negligible here, so I'll go through those numbers. But so you got like $40 in that same rubber as opposed to $800. Yeah, I mean significant savings. This is when you're taking your machines from huge maintenance operating costs to negligible lifetime design. Next. Oh, so today I went to Menards. I was looking at all this stuff. I was like, holy cow, we can print all this stuff. Oh, we can even 3D print that forklift. How? With wire arc additive manufacturing. So 3D printers, instead of a print head with plastic, you're running a welder head, a MIG welder head, and you can do large scale structures using that. And that's actually commercially feasible. There's companies that make those kinds of things. The windows, I told you about those windows. $300. Get yourself the panes instead for like $1 a square foot or a couple of bucks a square foot. And then you've got, $30, $50 in materials, like say $30 in glass, and the plastic is near free. So you're talking about reducing your cost from 300 to 10x. That's not. I mean, when I think about this, to go professional grade, this is $1 million project. To print a viable, maybe not $1 million, maybe like half a year it'll take you, but maybe a $500,000 proposition to get a professional code certified window that you 3D printed and used industrial process to do it. We can do that kind of stuff.
My mom has 29 windows in her house. They're all slightly different sizes.
Comments at the end. Yeah, no, that's right. Huge in our last home, $4,000, right? When you talk about now manufacturing these for sale, that's the $500,000 proposition. If you're gonna build this yourself, you don't care. I mean, they're not gonna be quality. They're gonna be like, they could be lifetime design, but maybe like if you don't have the tight steel, they will have a lot of airflow. Or if they're not, for example, argon filled, they have more conduction. But at a basic level, if you were in the tropics and or whatever, even here too, you can build yourself a multi-pane window. Maybe like you spend more in glass, so you actually put 4 panes of glass, no gas fill. Hey, you can still get a dirt cheap window that you can use yourself. Like I'm thinking about Suzanne, for example. If we didn't want to go the store route, and you're amenable to experimenting because you are, and we are, we want to do all this crazy stuff, you just print yourself a window and say, okay, I'm going to see how it works.
A round window.
See, there you go. So this is not so far off. If you're very much stuck in a current system and you're saying, okay, I can only do commercial production, I sell it on, to commercial builders, they're going to ask you, and even the bank is going to ask you, where's your warranty for your window? You have to justify all that. We will in an open source and get all the open source certification, but right now we're not there. And give me $1 million or $500,000 and we'll do that. But I'm just saying that the scale of development is significant, right? Okay, let's talk about insulation. Printers are actually pretty good at this because you can print multi-wall honeycomb very easily. That's not a problem for a 3D printer. A 3D printer can do any geometry whatsoever. Now that is a big problem for industry where they typically extrude that, because you cannot extrude a honeycomb structure with in a way that the same way that a 3D printer could. Like for example, you cannot extrude a tire that would have interior bubbles. That's impossible to extrude that. Because how do you do that? It's physically impossible. You can 3D print that. So in other words, 3D printing gets you this advantage of crazy geometry. So multi-wall, say you print something that's, a foot thick with a lot of airspace, but it's still got enough meat to be structural. You can be 3D printing structural insulating modules. That's okay. Let's develop that. Those are all possibilities.
Put them in the frame of the windows to help with insulation.
You can do panels. So for me, I would immediately think of wall panels that have even insulating, that have the electrical, plumbing, and mechanical locations or components built in.
And none of that horribly itchy, nasty fiberglass to do.
Right. But on another hand, if you know what spaghetti is in 3D printing is when you mess up a print and you're just printing randomly and it turns into this big hairball. But how about using that's similar to insulation? If you design a process for moving your head super fast and you're printing spaghetti intended for insulation, I think that could work too. I mean, we'd have to, of course, refine it and so forth. But I mean, that's not a crazy idea. It's just one of many things you could do. How about that culvert? Oh, very cool. If anything is 12 inches or less, you know how much a 12-inch culvert costs? It costs like $400 for this thing. So you can 3D print that near free because it's a perfect geometry. Like say that belt printer that we showed. Yeah, exactly. You print an infinite length tube and you don't have to go to Menards to do it. Then obvious things are, okay, PVC pipe. I'm saying, oh yeah, that's pretty cool. Corrugated drainage pipe. Yeah, that's easy. And even if you had a 1-foot printer that, imagine you make a 3D printer, which we built like this one. Let me see if I have it here. I don't have it here, but we built a 6-foot tall 3D printer that was, it's just one, it was actually an 8-inch bed, but it was 6 feet tall, because we could. It's, you can do that pretty easily, because we can. And therefore, well, then you can take a look at, for example, if you've got an 8-inch culvert, say you print a section and make like the last ring snappable together, so you can snap them together. So you're printing that in 6-inch sections on a printer that takes a 1 square foot footprint in your workshop. That's amazing.
6
right?
foot sections.
Yeah, you can print 6 feet on that printer, 6 feet tall. Because it actually, the way 3D printers work, it's easy to go up vertically because you're just raising the head and so forth. So very cool. Like when I see that corrugated pipe, cool. That's even if you have a 12-inch by 12-inch by 12-inch printer, print it in 12-inch sections, print a snap together ring. You can print this out of rubber material so it snaps together tightly and just connecting them together. So you got this amazing, that 12-inch culvert for near free if you get thermoplastic urethane at 13 cents a pound.
And those plastic culverts are as strong as the...
It depends how much meat you put in them. Depends how much plastic you're gonna print out.
Type.
And what type? Yes, I mean you can make that. You can make Schedule 80 pipe if you just have a thick wall out of high density polyethylene. You can make it very thin tube, like for this. I don't know how much you need, but you can make it light or heavy as you like. The drainage pipe, I mean that's really thin material, right? But underground, when you put it, like we actually put that under the driveway that we just made. You saw those sections there. That's 4-inch corrugated pipe. And I said, oh man, I looked at the price, the price shock of that 400 tube, and I said, oh, I could actually use like 6 of the small ones, and they cost actually 1/5 the amount of money, so that's cool. I just used those small ones, that the multiples. No, I mean they're good. They're meant to be driven over. They're structural. Once you get them underground, they don't get crushed because
distributes the load.
yeah. Okay, so let's.
Between the thing you were talking about earlier with the endless filament print versus the regular 3D printer.
The what print?
The endless filament. You
Yeah,
were
yeah.
talking about the endless filament. How's that different? Like when you're trying to
Okay,
make
so
piping.
you got to Google it, but you see some videos. But what it's doing, it's printing at a 45-degree angle, and there's a conveyor belt that slides it out. So you keep printing at this angle. It keeps sliding it out, and you can do infinite length objects.
I see.
Yeah, it's like that's pretty cool. That's really good for construction-related duties because you got a lot of long members that you need.
It
Plumbing parts.
seems like it would
Yeah.
mean that you could design completely different buildings.
Exactly. You now you have different tools, you have different assumptions, you can create a different reality. Number one theme of the art of possibility is it's all made up. Listen to that. Okay. Let's save the questions for the very end maybe, because we're gonna get stuck.
Sorry, I just wanted to make sure I understood that those
Yeah.
are two different things, but they're not. They're the same.
They're not,
thing.
they're the same, they're
It's
still
a different use of the same tool, is what you're saying.
different use of the same tool.
Okay.
And then, of course, you can think about now if I've got wire arc additive manufacturing, where it's a welder head, MIG welder head, doing that printing. Hey, you can print infinite long structures in steel. Cool. How about and then for if you talk about like a gantry-based printer, that would lend itself for wind turbine, like those megawatt scale wind turbine towers. If you can have the printer support itself on the stuff you just printed, so you can do. I see a lot of wind turbines around here, and I think a lot about wire arc additive manufacturing could do it because you can get wire. I mean, the filament cost even off the shelf is such that, well, off the shelf filament costs, they are like a 40-pound spool will cost you. Like the 20-pound spools cost like $50 or something. They're like a couple of bucks a pound. So it gets marginal for the amount, like the cost of that tower would be super large. But if you're now making your own filament or wire, Why? With the open source wire and rod mill. That's part of the Global Village construction set. Then you're talking about much lower costs because you're taking scrap and you're adding that value to it. Okay, so what else can we do with 3D printing? We can do rapid prototyping. Like, it's very useful for us. Like, this is not 3D printed, but this could be 3D printed. This is a laser cut model of our brick press frame, and we did that in a little workshop at a college. You can do rapid prototyping. We did like these laser cut things, but you can 3D print. I don't have the 3D print examples here, but you can do various little models for frames and other things. So 3D printing, you can print a scale model of the house. You can literally print, think about the house that okay, I mean, this is such a cool thing to actually do. We print all the modules with 3D printing. We practice putting it together on the table, and you practice the whole thing. So once you get to the real build, you know how everything fits together. That's powerful. So you can do that in real 3D printed prints that you print out your modules one by one. You can
So like adult Legos.
yeah, with real modules that we actually use, which are engineered and worth something. They're not like maybe like whatever various video games where the things don't correspond to reality. But here you're talking about if you correspond to reality, that is extremely powerful. And then you can also take it into a gaming environment where people can practice a swarm builds in a gaming environment if they can't be here. So yeah. So the construction material, I talked about a few things that this is an open source 3D printer called Lulzbot. We had a few of those. That's how you print. You can print in dirt. How about that? That's they made these huge. This was a prototype in Italy. They built this huge gantry to print in dirt. Now this is not too far fetched. I mean, imagine we're processing soil, we're mixing it, we're making it nice and fine so you can print very geometric structures. This is kind of looks kind of messy, but you can make it look quite good. You can if you add cement to it, it means you're literally printing walls, just like those cement 3D printers. But I think this is cool. Like if you went to Mars, you have a lot of soil there. You might want to print out of this when you go to Mars. So
That's what my class is practicing.
yeah.
Yeah.
Okay.
Going to Mars?
They have to pretend like they're colonizing Mars and make all their decisions based on
Yeah, there you go. So you can print houses like because you've got it takes a lot of material, and then it's very much insulating and it has a lot of mass and it protects you. So you can do things like 3D printed cordless drills. I haven't seen one that's actually a good one. This looks like that to me looks like just that's not a 3D printed drill. That's a piece of plastic. It doesn't have any components inside. But this is the perfect realm. Think about printing all the tools because all they are is a bunch of plastic, an electric motor, some steel integration, maybe some little electronic switch or this or that. I mean, 3D printing is so robust for that. And this is where the idea, when I mentioned the other day about houses that generate value, that don't cost you, but actually produce value. A little microfactory where you've got open design and 3D printing and some other tools can do that if you have the open design, which does not exist. And yeah, you build that in your, you put it in your garage. We got a 20 by 20 garage in the current model, perfect for that. If you want to leave your car outside, and then you can do 3D printing in metal. That's actually an open source version where all it is a platform that moves the actual MIG welder head there. What you see, that's stationary, and the platform below it is moving, so you can actually print three-dimensional objects in steel that might look like this, for example. What do? They did, no, they don't show any, they're not showing up. But this is the guy from Michigan, Joshua Pierce, who's now in Canada, in London, Western University. He's the guy that's hooking me up to a visiting professorship at Western, so I'm formally a visiting professor at Western. And we're going to start open source Ecology Canada and do some crazy stuff because this guy is committed. He's got huge moral intelligence regarding 3D printing, and he publishes like mad about all kinds of open source design, and he's getting into greenhouses, and we're probably going to develop the open source inverter because he's good at electronics. Yeah, so RepRap, so that's this is how it started, like in whatever it was, 2001 or something, where the patent ran out on 3D printing. So these guys built their own 3D printer based on an expired patent. That's the parent and child. That's how it started, and it turned into, I would say it turned into a huge industry, probably like a $500 million industry based on this, because so many people replicated it. All these companies started, and some of them went proprietary, and it was big fiascos and stuff like that. But yeah, I mean, you can say that 3D printing is one example where it has changed the economy, because just about anything that works today as a 3D printer is based on this, all the know-how, the firmware, the software, the electronics, mechanical designs. I mean, they're based on all this stuff. And so this is, nobody noticed though, and it hasn't really, I would say it hasn't, because the idea would be that, oh, now it's showing huge economic impact, but it's not, because there's no design, no open design. Give me one useful 3D print. There are, of course. There's plenty of useful prints, but not, yeah, but not to the level where Amazon is history. That's the point, people. That's what the RepRap project promised. They said, we're going to change the world because we're going to get the cost of production to zero. They're another zero marginal cost society proponent, right? None of that has happened. Like, if I have to get an ozonator that I could, make myself from simple little electronic thing, and maybe a 3D printed case or a metal case that I get from Amazon. No, I keep buying them because I don't have any plans, or like there's no plans out there. There's no plans for a good cordless drill, a saw. Think about how easy that would be to make. All those components are completely available. All the motors, little bearings and shafts and machine parts. It's all highly available, and you can then take, or even you can take the stuff that breaks here. That's why we're saving a whole pile of broken tools. I mean, we have a huge pile of broken tools in the solar cubicle there. But we could then take that, and if the design is open and meant for repair and reuse, those tools don't live 1 year, they live 100 years. That's a huge difference. Like, everybody's missing this. All these people talking about changing the world and regenerative economics. Where's the open design for consumer goods, like 3D printing and this? Like, nobody talks about that. It's so pathetic in some way. I mean, it's so hard for people to jump out of that current mode. I mean, it's new stuff. It's only a few years, a decade or two now, but the world's takes some time to catch up to the possibility. There. Next. Yeah, the 3D printer is one of the Global Village construction set machines. So is a shredder. There's a shredder in here. There's a bioplastic, I call this the bioplastic extruder. That'll be our filament maker. Those tools are in here. Yeah, so 3D printer is a big one for doing all kinds of stuff, right? So 3D printed lumber with, the way it works right now, you can get like 30% of sawdust into plastic, and that works really well for lumber. I think insulation we could do. You can print definitely in concrete like we've seen before. Glazing, like you can 3D print polycarbonate, for example. Do you know polycarbonate? It's a super hard plastic. That's a thermoplastic. That's a perfect case for multi-wall glazing. Glazing. Did you hear that? Glazing. I want to show you that right now. Look at what we did the other time. Oh, so you go. Ooh, how do I go back though?
Little arrow bottom left.
Oh, there it is. But why wasn't it working? I do have a. Oh, left. Oh. Why isn't that working? Oh, there it is. Okay. Design that in FreeCAD. Oh, my buttons for some reason are freezing up here. Okay. What is that? Anyway, I mean, this is a print. This is our own print. That's just polylactic acid. But if you make this out of polycarbonate, you can print multi-wall glazing like that, which is pretty expensive. That stuff is pretty high tech. But you can get waste filament. Once again, waste plastic and polycarbonate, 10 cents a pound. So that makes a really strong case for that. Let me see if I can. Oh man, my computer's freezing up here. We went from FreeCAD, super easy to do, slicer in Cura, 3D printing software, to the print. There you go. Or you can do like this guy's printing these 3D printed towers, but I go through a lot of examples of what you can save on. Okay, let's go through some more things here. Yeah, I mean the 3D printer is pretty huge in that with the 3D printer here, let me maybe go back to present. With the 3D printer here and the CNC torch table, the CNC torch table cuts steel. We can cut, 1-inch thick steel we typically cut half-inch steel, like say for structural parts. You can make all the parts for various machines. 3D printing, you can do all complex geometries. So metal plastic composites are a big idea. They're a big deal. The way we do it is with the universal axis. So our design has these very modular axis elements that can be used for building all kinds of geometries of CNC machines. We did things like magnetic mounts. I think this is a decent idea. I mean, you gotta make sure that this thing sticks onto whatever you're holding. We did these axes that were actually mounted with magnets to the frames. That works. It's not as robust as bolts, but that does work. You can do large or small scale machines. So for example, we built, steel. 3D printer for steel. Here this machine, like you see those 3D printed parts there, that's how we join the metal tubes together. So you can get those complex geometries out of various machines using 3D printing, and the rest is steel. And that's a perfect combination of plastic and metal. So metal plastic composites of all kinds of shapes. Like all those, that's 1-inch universal axes with 1-inch rods. Those are 3D printed pieces, those ones, which otherwise would be very complex to machine. Like they have a lot of complex geometry. So 3D printing is very useful for that. Or like for the cable chain for the actual oxyacetylene fuel hoses. This was a CNC torch table that we're making. We ran that, we cut a couple of things. It didn't move around good enough. Like once again, this is the heavy development that needs to happen. We built this 6 foot by 6 foot by 6 foot 3D printer. Here we're looking at the heated bed. That didn't work. We couldn't even get the bed up. It wasn't designed properly. It takes engineering. We did a first prototype. It was cool to see the big shape and the fact that we could move it slightly here and there, but with a few people working like for a month on it, like you don't get too far. As I said, like any big development, you're talking about serious commitment and resources. You can scale. This is what I'm talking about, multiple print heads. So you can be printing, for example, 9 of those. Like you see this 3D printer here, it's got those. Those are 3D printed, all the 3D printed parts with metal, but you're printing more of them to make more of these machines. So yeah, multiple print heads on the same printer work as an idea to scale up the speed, because recycling local materials with 3D printing is possible. That's how I think that if precious plastic got onto that wave, I think they would have done much better. If you guys know about precious plastic, it's a plastic recycling project where they developed open source shredders, extruders, presses, but not 3D printers. They somehow didn't go into 3D printers, which I think that's completely eliminates the huge potential of plastic reuse. I think they completely missed the boat on that, is my critique. Because then you're talking about now precious plastic is perhaps one of the best open source projects out there. Their traction is bigger than ours in terms of involvement. They're doing like simple kind of artistic or other 3D plastic recycled things using the machines they have. They do have a good traction. I mean, there's probably 100 of their machines around where they're actually processing tons of material every year. So that's pretty cool. But it's not at scale. If you talk about scale, you're talking about billions of tons, and that's the kind of scale we would talk about. Like millions of tons and billions of tons. If you talk about a single house, if you're talking about replacing, like we're talking about 5 tons of material for a single house, that's probably the entire mass that precious plastic would do in a year, or maybe, we're talking about 5 tons a house, and with a crew of 24, we can build, a couple of dozen of them. Talking about 100 tons that we would need just for our program with 24 extreme builders from the Future Builders Academy. 100 tons once we develop this. That's us. $1 million to get there. Yeah, let's do it real
Okay.
quick because the return on investment is huge. You invested $1 million, you can replicate. I mentioned that 30,000. That's our figure. For that 30,000 figure was for a house every 2 months. Now you can definitely scale up the. You'd have to scale up the printing infrastructure to get more and more, and so forth. But we're talking about not. This is not some multi-million-dollar, billion-dollar, custom manufactured home facility. This is a 4,000 square foot workshop in the middle of nowhere, Missouri, and Africa and North Pole and Mars that has succeeded in distributed manufacturing for the universe. Right, I mentioned about the power of 3D printers, CNC torch tables as a combo. Let's look at some of the workflow here, the tool chain. You got to grind waste plastic, you got to shred it up into little bite-sized chunks so that they would flow in your thing. Like for example, if you've got a filament extruder, you can't just throw any random stuff in there. You got to have flowable material. You got hoppers, you need flowable material. So you need a shredder, the grinder part. Then you can make filament that's effectively an extruder thing, pressing plastic while heating that plastic. So it's got heater elements. It's basically a tube with heaters and a screw inside of it. Even a drill, like a drill bit, like a 1-inch drill bit, the long wood ones would work for that extruder. People have built stuff using that. It's not professional grade. It won't get you high quality, but like reliability. But you can do it. You can do simple extruders like we have. It just had the extruder we built had a 1/2-inch auger bit, one of those long, like 16-inch wood auger bits. Okay. Plastic filament is not affordable for larger objects. Off the shelf, it's about $8 a pound. So like, you get the lowest cost filament is around there. You get a spool of filament, which is a kilogram. It costs you like $16. You can actually get it down to like this figure can maybe as low as $5 a pound if you get it in mass. But then, I mean, you're not going to print your wall module. Like one of our wall modules weighs 100 pounds, let's say. So if you paid even $5 a pound, you're paying $500 for a wall module. No, that's not affordable. That's at least 5 or 10 times more expensive than lumber. So no, that doesn't work. So you got to go back to regrind of waste plastic. The easiest source is plastic bales, which cost 10 cents a pound. So that's the figure. Garbage bales, like at recycling centers. Now they would have to be graded. You'd have to have specific plastics that you're working with. Or you can get down to, I mentioned plastic recycling online marketplaces where I saw thermoplastic urethane for 13 cents a pound, and they had tons of it. Like they had tons available every month. Like a lot of tons, like 100 tons or however many tons. So it's accessible in a replicable way. Now, electricity costs are, if you use from the grid electricity, it costs you 50 cents in electrical to do it. You can review this. I'm not going to go into details here because I'll bore you, but if you're using electricity from the grid, it still takes you, even if you have, say, free plastic, it would cost you 50 cents a pound to print it, because your filament printer heats the plastic. It has to melt it down and then deposit it. And you typically have a heated bed, and there's electricity use. But it can be reduced to about 3 cents per pound. And how do I get that? I'm talking about solar, where the realistic cost of your solar system, Suzanne, is you're going to be getting electricity, like when we paid for those, what you paid from those panels, is going to be about about 1 or 2 cents, less than 1 cent. I have those calculations. Look at the CDCO Home PV system on the wiki. It's less than 1 cent a kilowatt hour. At that point, it's real. Look, you gotta study those numbers, and I'm not gonna talk too much about it because I'll bore you in the detail. But then you're talking about 3 cents a pound printing cost. So use ChatGPT, go through 3 cents a pound for the objects that you're printing. Yeah. So how much does a wall module?
Incredibly.
So if you got 100 pounds times 3 cents, you printed a wall module at $3. This is
Most cities don't have anything to do with their recycled materials that they gather. Like in Austin, for years we followed the recycle trucks. They literally were dumping them just in a different section of the landfill.
Yep.
Yep.
Wow.
So
There's nobody buying it.
So zero marginal cost society promise, it's realistic from first principles if you have access to renewable energy. It's funny that the grid cost still remains at 10 cents and it always will, and it probably will go up, even though you got things like solar. People haven't figured out how to store solar, and that's why we're doing the thermal battery and things like that to usher that process along, things like that. But
Can I just share one thing about that is, until recently, right before we bought this EcoSeed home, in order to bring electricity, on-grid electricity back to that area of the campus, it was going to cost us $15,000 to $20,000 to bring it back there. But
yeah.
for $60,000, we're putting in a whole house that has its own full supply and probably enough to power most of the things that need to happen back there.
Well, all at night, at daytime, but what do you do
Right.
for night?
Oh, we just plan around night.
You can do that, and once you're willing to live with the sun, which is called biomimicry, you get to say that PV and renewables are real. Right now, society doesn't believe that we're part of nature, and therefore they say that PV and renewables are not feasible right now. Nobody has solved
You
it.
watch the
It's
fire at
propaganda.
night.
So anyway,
The TV.
efficient printing. Yeah, so I just went through some numbers here, but if you want to print a 2x4 piece of plastic lumber for your deck, 10 pounds, it would cost $5 in electricity alone. So it's kind of getting to impractical if you use regular grid electricity. So I'm just going through take a look at this. Let's see, if the bottom line is, if you're going with solar energy, you're getting to zero marginal cost, right? And then, okay, well that's 3 cents still. How do you get those PV panels to go down even more? Yeah, you can. Like once you create infrastructures in the open sector where you've got microfactories that produce the PV panels from sand using PV panels that you already made, because the payback time in energy for PV it's a few months now. Some people say, oh well, PV never pays back because there's so much energy that goes in. No, that's absolutely not true. It's a few months right now. So so that means that is a case for, we're talking about abundance in society as the norm. Okay, so the thing about 3D printers, they're kind of slow, so you got to look at how you scale that up, and I kind of mentioned that. Oh yeah, so actually super volcano nozzle, I did not say that right. They do up to 20 pounds per day extrusion rate, if I'm correct here. Yeah.
If you're pushing it as fast as humanly possible, yeah, you can get about 20.
Yeah, but the more realistic, yeah, good. So you got maybe less than that. And I think I said 5 pounds per day. But then that does not preclude us from open sourcing the super volcano, the next iteration of that, which can do more. I think there's fundamental limits to how plastic flows, to how much you can do, but I'm sure there's some creative solutions around this. But the simple way around it is you can go into multiple print heads as one way if you're doing plastic, or just print heads that are just monstrous size print heads, not the small ones, but like you can scale this up. That's just a question of R&D. Let's see. Yeah. Under 0.2 cents. Wait, what am I doing here? Why did I say? I'm getting lost here. Because I said, I don't know what I'm talking about, so I'm gonna skip it. I got to review this. The bottom line stands. Let's see. Super volcano. You take about 140 watts. That's the energy use for a super volcano nozzle. 20 pounds printed equal 3.5 kilowatt hours, or about 6 pounds per kilowatt hour. Why did I say that super high cost of 3D? Alex, do you see what I missed there? I'm not sure, but here I'm concluding 0.2 cents per pound energy cost of printed plastic. So energy cost of printing is this is for real. I did go through this. I'm kind of losing myself here today. I'm going brain dead. But the bottom line does stand that
providing your own plastics, right?
Yeah,
That's
if
because you get the filament down to so cheap.
we're talking about just plain energy cost, and it's ridiculously low. So compared to material cost, it's effectively free. Let's run with that, but do go through this in detail and actually correct me if I'm wrong. Now, is it cost effective? Well, 5 cents cost per kilogram. I'm gonna skip this because why am I contradicting it? What's the difference here? 0.2 cents per pound energy cost versus 5.
That was grid versus OSE.
Okay. Grid versus OSE. So if we have now just grid electricity, we're talking about thank you, Alex, 5 cents per kilogram. And if you do the OSE PV system, click on that link. OSE PV system right here. Go through it. How you use things like freezers that are off grid and other things. This is the PV. That's actually from the CDECO Home 1. That's that. But take a look at that. I go through the very concrete numbers of what we paid for the photovoltaics, how much life they have, and how much energy they produce. So in that scenario, we're at about 1 cent per kilogram or such. So energy cost of producing filament is negligible. This is actually the filament extruder that we used. All it is there was a hopper on top. This is your bed of your little chamber of pellets. There's an extruder that basically that auger, half-inch auger inside that heated tube. It's heated with these heater elements from the in the tip of that. Oh, it can't go. It's not. Let me go back again. Just so you can appreciate how that thing works, because basically you're taking that exact simple prototype that I was showing there, and now you have to talk about how do you scale that up. Well, you have to have a bigger tube, bigger extruder, more heat controls, zone heating, so you're very precise about how you're controlling it, but the idea is the same. Here this worked and we produced a whole spool of filament. Took us 2 hours, and that's awesome. But the same concept applies. Shredder to extruder. This discusses the home scale print cluster. So I basically stating here that multiple heads, multiple printers, and I went through that already. About 500 pounds a day from that cluster of 12 printers with quadruple print heads at a conservative rate of 5 pounds per day. I mean, that's quite doable. 12 printers, that's a small room of printers. You can stack them vertically. 2, it will take hardly any room. And here I go on to this example of the 3D printed polycarbonate glazing. Now, what is the problem statement here? So I think for anybody that's watching it, to appreciate the big deal about this is people, let's wake up to displacing Amazon and Walmart with 3D printed, open source, everything stores. I mean, I call it Google. Go on the wiki. I talk about the open source everything store. These things are so simple. This is basically your slave labor in China producing all this stuff, but all those components are available. Right now, China produces most of them, but open source them, produce them locally, combine 3D printing and metals to do this. If you talk about larger scale printing to clean up the environment from waste plastic, yeah, you could be making a lot of house parts, but in order to get there is a very focused development effort. We're going to do it if nobody beats us to it. We have an ambitious plan to do so because we can be saving $20,000 per house in material costs. So we are very serious about reducing house cost and developing these 3D printers through a dedicated open source collaborative process. So at that, I'll stop and let's go to questions. Or I want to introduce Alex, who's on a remote session where I would like to I would like you to share with us what's the latest status. What have you done for in OSE's work? Because Alexa prototyped the next iteration of the 3D printer. Tell us the update. Where are we at?
Yeah. So, hi everybody. I'm Alexa. I've been contributing to OSE for a couple of years. The first thing I actually think I posted up on the wiki was the D3D Mega version 23.05, which would be May of 2023 was the first contribution. So I've gotten to poke around with the machines for a couple of years, which has been fun. Current work, I have built and almost completely documented a 3D printer that's based on OSE's older designs with a couple modifications. Primary one being that the newest version has a plastic and rebar composite frame, and I'm adding a system to it where you can use kind of like fencing wire, sort of like electric fence wire, to tension the whole frame together, especially by making like little crossing little X's in the wire on each face. And I'm hoping all of that will make everything nice and rigid, keep everything nice and square, which will help the printer in its performance. Because as it sits, here's something I made for a friend of the family. This is just like a little glue bottle for some arts and crafts, right? And I needed a plastic holder that it fits in. So, this is right off the printer I already made. It's got a few simple imperfections and things to it, but whatever. It's a functional part. It works. It's strong. It'll probably last longer than I will, and you can do these all day long. I've printed so many things. I have forgotten more than I remember at this point on that machine. So definitely usable, especially for stuff that you're going to just put in the wall in a house. It's great for that. So as far as upcoming changes, to get to the kind of quality we need high reproducibility, right? And actually, as it turned out, Marcin's point earlier about like docs and quality control, that was actually the majority of this project. For me, it ended up being the 3D printer building and thinking about the different little unique design challenges for that. That was the easy part. So the quality control and making sure that you're having very, very repeatable, consistent, accurate results is actually the more difficult piece. And I feel like that's a little nugget that'll probably carry through to most of the different open source hardware and software work that we do. It's making sure that across the entire distributed manufacturing world, that everyone can get the same results from the same knowledge and material inputs. So a little tangent there maybe. But as far as the printer, looking on upgrading the frame a little bit more, and then the universal axes and things I haven't really had to change. I added a couple extra components to the controller, so there's like a Raspberry Pi computer in there so that you can have a web portal, you can log in remotely to send prints, monitor the prints with a webcam, that kind of stuff. And I see that documentation pulled up behind Marcin there. That's a little picture of it. It's those corner connectors are kind of the first stab I took at, or maybe second or third stab I took at building the plastic composite frame. I'm actually going to be making one that has way more. Actually, might even have one handy in the other room. Let me go wander over and grab it. But the machine, it's going to be great, honestly. Here's another one. This will be helpful to show. Let's see if I can split my camera around here.
Let me comment before you go further. So, if you look at this, what do we do there? We just replace the frame that we used to CNC cut from flat sheet with rebar. How great is that? That's awesome. And it's super stiff. You got to make sure the corner pieces and everything is stiff enough. But I mean, look at this. So now anybody who has access to rebar can make a frame in a second. Before, cutting the frame was a big deal. We actually had those flat sheets of metal that we cut basically 5 sheets, actually 6 sheets, because a cube has 6 sides. We cut those and welded them together. So now we're not welding and not cutting, just rebar. Bam.
Yep.
That's all. To me, that's awesome stuff. We're replacing like more complex things with stuff that still has the functionality. Rebar is 50,000 psi strength, and it still works. So there you go. So that's like simplifications. We like that kind of stuff, and that means you're reducing the cost even further of a printer like this. Mhm.
Yep, and making it lighter and more robust, easy to repair, all the good stuff we love.
Yeah, exactly. Alexa, what were you going to show?
Oh, this is
Okay.
my testing corner piece. This has some of the holes through it. You
Uh-huh.
can kind of see it here on the back. And that's
Yeah.
where you can run the wire through.
For tensioning.
And then I have like just little examples of it there so you guys can kind of see.
Yeah,
And then this is a whole bunch of fastener holes so you can just
Ah.
fill the whole thing up with fasteners, keep everything nice and tight.
Hmm?
So yeah, makes it nice and robust.
Yeah.
That's,
No,
I hope
that's-
that's the dream anyway.
That's very cool. I would see that the tensioning would be quite relevant for much larger machines. In the smaller machines, I would just print the corners fatter, just way fatter, maybe. And yeah, we'll see. We'll see. I mean, this is exactly it. It's like I can talk about all I want until I actually print it and build it. Like Alexa, like I'm just talking. So Alexa's providing some real data. So that's great. That's a great contribution to. And it's all fully documented on the wiki, so it's all good. Where else? Okay, so thanks, Alexa. What else? What other questions do we have here?
I had asked about how the weatherization on
Yeah,
it versus the wood and the 3D when we were talking about.
weatherization of.
Like if we were using it for floorboards, you were talking about, and rain hitting it versus on the treated wood.
Well, the advantage of plastics, a lot of plastics are that they're, a lot of them go through UV degradation outside, but there's additives that people put into plastics to make them last for a very long time. For example, things like
Trex.
foundation, 3D printed instead of using the treated lumber. That's a great idea because it never sees the sun. It will last forever, and it doesn't rot like wood.
Right.
And they have those
So-
Trex boards. It's basically plastic lumber that you buy. It has special little adapter tools for it that you use. We framed a porch out of it in Florida. It's super expensive and kind of hard to work with, but it's got like 100-year lifespan, and it's totally basically 3D printed plastic. I don't know exactly how they make it, but it's essentially plastic 2x4s. Is what it is.
So this piece of plastic,
Trex.
which is 2x4, only 4 foot long, is $12.
Yeah, that's what I'm
But
saying.
it-
is
Stupid
it
expensive.
also reusable? Could you
Yeah.
put that back in your
Oh, yeah.
shredder and make something
Yep.
else with it?
So
Yep.
your waste you're reusing, unlike these
Yeah,
little pieces of
that's-
wood, it's like
That was one of my questions.
Well, yeah, absolutely. But here, but that's the thing. Like right now, this would probably, after its use, it would end up in a trash heap in
I have a
a landfill. For us, the cool thing is because we have the technology or know-how and infrastructure to recycle, we're making the closed loop material cycles
so there
happen.
is no waste technically.
Yeah, zero
I have-
waste. I mean,
I have
yeah,
a question related to that with the 3D printing of, say, using 3D printing a 2x6 on one side of the modules, because you said when they're doubled up, you effectively, one of them doesn't have to be structural, probably at least on the first couple floors.
Mhm.
That's essentially because the sill plate is spreading the load across all of the 2x6s, right? So
Yeah.
that second one is just redundant, and it doesn't need to be load bearing,
Yeah.
even though it's taking
yeah.
because the other sill plate's bridging it, or 2x6
Yeah.
basically.
Yeah,
across
it's
the
like
top.
that, and we'd have to get into the details of the calculations, which will be another session.
How does it play out as he's talking about a 2x6 plastic board versus a wood board when it comes to like fire?
They both burn, and
Exactly.
plastic's going to be worse, and plastic's going to start melting before it burns.
That's
So,
right. That's what I was
so you're going to have disadvantages thermally, like if you use certain plastics, and you don't want to use it structurally where it's in any hot kind of area.
like
by
so
all
no
means.
kitchen.
But they do make microwavable plastic, right? So I'm sure we could look into some. I mean, I don't like to use it, but
Right.
they have,
Yeah.
Melamine.
Yeah.
they have cooked plastic, like
Yeah.
boil in a bag stuff,
So,
like it's
yeah,
disturbing,
exactly.
But it must be hot
There-
plastic with high heat tolerance.
There are limits, and then so they have, like for example, some computers or electronic cases have fire retarders. You have UV retarders. So
Don't they have a paint now that's got fire resistance?
you can do either coatings or embody it throughout the plastic itself. So there's all kinds of ways, and this is all kinds of
Yeah.
stuff that we have to figure out
Okay.
to make this
There's-
happen.
There's additives for paints. Essentially microscopic air bubbles that you mix in the paint, so it makes your paint insulated. I wonder if we could do the same kind of thing with like window frames and things like that.
Interesting. Yeah, like so. What is that foamed plastic? I mean, that, like, for example, polystyrene is foamed plastic.
Right.
So if we get good at this, at popping plastic like popcorn, we can make polystyrene. Polystyrene is a thermoplastic. Did you know that? So we can do. You're thinking divergently here, which is cool. And yeah, all this kind of stuff is. All this kind of stuff is possible. You got to figure out how they do it. Like, not how they, but how we would do it in a different way. I mean, how? So you start with, you take polystyrene. How do they make it pop? It's something about temperatures and pressures or whatever, steam or something or whatever. And we could do all this kind of stuff here. Like maybe design a printer that prints insulation like that. Whatever.
Well,
I mean, whatever.
Okay, that was one of my questions. So piggybacking off that. I was looking, and you were saying that these printers, they can print. Some of them can print like plastic and mud, and even cement. You were looking at those, right, extruder pipes, like the way where we're talking about, and this filament. What about things like ceramics or things like that, where we can actually use the dirt?
Okay, so for that you can go into laser selective layer sintering kind of 3D printers. What they do, for example, give you a good example of what you can do right now. If you have a powerful laser, you have a bed of sand. What is sand?
We do have a bed of sand.
What is sand? It's silicon dioxide. It's what glass is made of.
Yeah.
So if you now throw a laser and do your pattern in it, you will sinter it. You'll make it come together. So, and then layer by layer, you basically go wipe with another layer of sand, wipe. So wipe, laser, and over time you get three-dimensional objects that are now glass. There you go. So you can do ceramics. The way they do metals and like ceramics is what you can do there is the powder thing. Well,
or fix the head and move the body.
So let's talk about selective layer sintering as a super high-tech way of 3D printing. But there what they're doing is very advanced powders that are very, very tiny. Like a powder that's, for example, plain steel or plain stainless steel, but it's micronized. And therefore, stainless doesn't rust, but all these kinds of things, when you do that, because of oxidation, when you hit it with a laser, you have to typically do it in an inert environment. So the technology gets funky here.
Basically.
Yeah, I mean, you could do gas shielding just like MIG welders do gas shielding, so you have a super clean weld, right? It would be a chamber that you're just pumping
what about
argon or whatever.
For the size of the 3D printers being an issue, I was thinking about 3D printing homes and stuff, and they basically just 3D print the walls, but couldn't you put essentially instead of, so you've only got a 1-foot box printer, but you could put it on a motorized 4-post module that you could remote control and drive around, right? So you could 3D print one layer at a time and move it and just move it from one wall segment to the next, and you even have like
the wall where it belongs.
And that was my question is
you can
I
do
was
that.
looking at which types of 3D printable material are also breathable. So far we have mud, which is breathable, because really you don't want your walls plastic or steel or any of those things. You do want the walls to be breathable. You want your foundation to not be breathable, right? But you do want your walls breathable.
They're doing 3D printed mud homes with it looks like
mud foam?
No, it's literally mud, and it looks like 3 balls essentially. So it does it in blobs, and it's pretty incredible. I forget the guy who's doing it, but I can find out.
What do they do for inside each one?
It's just solid
together.
They stack on top of each other, so they do layers of them, and it basically forms a wall, and then it would have little divots in it.
That's
so then you would basically stucco over it or mortar over it.
Now we're doing like spray foam, right? We do spray foam insulation, but we also do
That stuff's
drywall,
nasty.
right? That is to hold things in. But I'm looking at like, what about walls that are insulated? What if you had, wood or something other, but you still want something breathable for an insulation, but you want it to be a natural breathable material? Could you remember we were talking about foaming up plastics? Couldn't you foam up mud and like have it be like a honeycomb kind of a mud where it actually has more air trapped in natural materials?
There's aircrete. Yeah.
Yeah.
Like right, but
Just
instead of
felt
being waterproof, it's still breathable material.
Hempcrete.
Like, because you want something that lets both water and air slowly
Yeah.
pass through it.
The answer is, yeah, sure.
Great,
Someone's got to develop it.
no problem. I'm
I
on
mean,
it.
there's no physical
I'll work
first principle.
with your dad.
Yeah, you can totally.
Brad, what was your question?
I was just wondering about degradation and like, should we be worried about like microplastics, or is this the way to encapsulate those, or how do we address that?
Well, if they're protected, I mean, microplastic is from degradation, where you have typically like UV is the biggest, I think, killer.
It's in all our blood anyway.
If you-
already, so.
If it's in a foundation, it doesn't. If it's covered from the sun, you get rid of most of that. Then you would have to study, well, how much does it oxidize? Like, for example, polyethylene does oxidize, and yeah, I don't know the
for
explicit answers to that,
Okay, I
but
was just curious.
I mean, some things are, plastics. Like, for example, when they have the geotextiles, which are PET, I mean, they say they'll last for many decades. Like, I think I've seen things like 7 decades or something.
Car tires with the
50 to 100
with
years.
the off-gassing. A lot of people are worried about that when it comes to airships and using them in their walls. But actually, most of that off-gassing occurs in the life of the tire when it's on the road and exposed to the sun. So by the time you use it for your home, it's basically done off-gassing, and then you're enclosing it in stucco and mortar, and so it's not getting exposed to the sun or air.
That brings me to one of my other questions. Rubber.
That's what I was just gonna
If
ask.
you're gonna say, I know that we currently recycle rubber just like by shredding it and using it in a shredded form. Is there not a way to make it flowable again?
Like,
Thermoplastic urethane is a rubber, which is a plastic. It's a thermoplastic.
But from like car tire.
Yes, you
rubber?
can do, if you micronize it and blend it with other materials, like even say polyethylene / micronized rubber blends, you're going to get some of the flexibility back. Yes, you can use it as filler, just like you can use 30% wood dust in 3D printing filament
The
to
problem-
get actually
So-
rubber properties.
I guess what I was looking for is, remember we were talking about remaking our own tracks, like the thread for the machines and stuff, but you couldn't 100% reuse rubber. You couldn't like take your own treads and mulch them and put them back in and reprint your own treads from the same rubber.
The problem there is that rubber is thermoset. It doesn't.
Yeah,
It's not
okay, that's what I
thermoplastic.
thought.
And the other problem is that the steel belted radials that they put inside the rubber tires make it really hard to get to do something with the rubber, because you've got steel inside it, and then you have issues like melting it down, and like it's a big
Separating.
process to separate the
Yeah.
metal from the rubber.
Not if you have the open source industrial shredder. That's not too much an issue. It's a physical processing issue.
Okay.
Well, there you go.
So we would need to know where the point of plastic versus how hot it is before it lets out anything that we wouldn't
Yeah,
want.
and don't be using it where it's in places that are sensitive like that. Like,
So
feel free to use it on a deck, your landscape block, like
But that's gonna be
pervious
out in hot
pavement.
sun, but it's also
Oh yeah, it's also sun. So those things, you would have to make sure those surfaces are UV protected, stabilized. And they do make. I mean, there's PVC like that gray PVC. That is. That lasts
outdoor. Yeah.
for decades outdoors. Like the stuff they run electrical wires on power poles, like those tubes. I mean, they're there for decades. So
How much do you think it would cost to get the process set up to be able to fill our windows, single pane windows, with argon? Is that a big issue, and how much of a benefit do you get from that as opposed to just air?
I don't think that's a big deal. You
Right?
got
It's just a gas, right?
So think about this. The one way to do
How is it?
injection. Well, if you have okay, thought experiment. 3D print yourself a rubber ball that's empty inside, stick a needle in it, and pump argon through that needle. But you have to have an exit hole, but eventually you pump it full of argon and close that other hole, and you've got, okay, how expensive is that going to be to scale it to industrial production?
I have no idea.
No, not too bad. I mean,
It's
the
reasonable.
device is,
But
this
do
is
you
like
think the
very reasonable. I think
do you
it's very
the
reasonable.
benefit of argon is it so much better that it's worth the added expense?
I'd have to look at any reality on that.
Oh, and then another question.
I don't know the answer to that.
Another, I know a guy, Sean and his wife. They were trying to have an earthship built in Mayaca City in Florida. It was a disaster because the guy that did it was incompetent. But anyway, he's a civil engineer, and he may be able to help with certifying some of the 3D printed parts, and maybe we could get them.
If he's willing to
a
do it,
CD
bring him on.
a
That-
CD
it takes
go
some,
home. Maybe we could do some sort of exchange where we, because they basically got screwed out of their house. They spent a lot of money and got ripped off by this guy. So they need a home, and he's a civil engineer, so I could talk to him and see what.
Bring him on. I mean, if he's willing to be a rebel, meaning that he's going
I
to
think he
certify
is. He almost
reference
died not
designs
too
for
long
open.
ago. That has a way of opening people's eyes.
Bring it on.
All right.
Yes.
Seriously, I'll talk to him. And then plastic culverts. You already answered that question.
Uh-huh.
And then, I was gonna say too, like one good option for getting lots of plastic in bulk for free is contacting some of these cities, like
Yeah,
the
that's
city
what
of
I was saying
Austin
the other day.
and their recycling
course.
centers.
Of course.
What are they gonna do? Like they don't.
Yeah.
That's a big problem with recycling here in the States is not having anything to do with it. They don't know what to do with it.
And some
So
people
they run these platforms of recycling programs to make everybody feel like they're being green, but then they're like, oh shit, well we don't have anything to do with it, just put it in the dump and we'll hide it and dump it in a different part of the dump.
Thank
And
you.
it's pathetic, but it's the reality that's happening. At least it was in Austin, Texas 7-8 years ago.
So now you're talking about taking a waste stream and even making it a revenue stream.
Right.
Yes, today I was driving to Menards. Some farmer had a huge stack of broken concrete. So I thought, pay me to take it away, and I'll actually,
Yeah,
make
that's
gravel
a big,
out of it.
That's a big deal.
Well, that's just gonna
Yeah.
say. There's towns where you pay to recycle.
yeah.
You're paying, so they wouldn't have to pay if we're just taking it, and then we benefit because we're using it. It's like a double.
And
It's
then,
true. That's called enterprise. Yep. There's unlimited wealth out there if you can only see it.
So
Some people might see like a
I made those.
trashy field filled with weeds. I see abundant gardens dripping with fruit. Man,
And enough energy to send stuff into the moon.
yeah. From every acre, you can generate hydrogen to send a person to space. Every acre, so we can have a
Enough
spacefaring
hydrogen?
colony on our village of 1,000 acres.
Say that again. Now what?
Every acre?
Yeah, you can go into space if you capture solar energy and generate hydrogen to fuel your rocket. In 1 year, you generate enough of that fuel from 1 acre to go into space. In other words, a civilization
have
as
that.
small as 1 acre can be a spacefaring civilization.
So
But
don't-
you'd have
why
to
don't we
cover.
do that with
You'd have to
cars?
cover the whole thing with
Do what?
solar, though, right?
Take
The
that
entire
energy.
acre would be one giant.
Take that energy,
To-
make the fuel for cars.
Yeah.
We're gonna do it as soon as we get to it.
Okay.
I think
No, I'm
Japan
just
already
saying, not
uses
everyone's gonna want to go to
hydrogen
the moon, but we've got plenty of
I was just saying the
vehicles.
extremes,
No,
yeah.
I get it.
Yeah.
I'm just saying,
So-
no.
The bone loss isn't worth this trip to space. It,
You
like, really. Like most astronauts, they have really, really weak bones, and so they got fiddle like you need the gravity, and so when you get in space and there's no gravity, your body's like, my bones don't need to be as dense. I'm going to consume some of this calcium, and then it gets back to Earth, and they're like, oh
Okay.
shit, sorry, your bones are weak as paper now. And
Yeah. So, any other main questions, and
Yeah,
we'll
we
wrap
We're
it up
talking
here.
about 3D printing metal. Are we even going to do like screws and nails and like?
Yes.
We wouldn't need to buy anything then. It's
Yes.
all completely. Okay.
Yes, all of the above.
When are we starting and where are we starting? We're talking about.
Well, by
still-
2028, we'll be able to do things like engines, bolts, parts, all of that. That's which is part of the Global Village construction set.
Can I
Go through all the machines there. You've got precision machining, you've got production and rolling of metal, forming of metal, and all kinds of processes where with $50 million and 2028, we're there. That's a
What are we talking
major,
for,
major
like,
effort.
Once this is done, our 14-day, like, what's our first step to do next to get there? Like us individually.
build the big house. Build the
Well, we're gonna move the house over to Suzanne's place, and we're gonna start working. Like some of the development will be around the open source skid steer, but the build work will be. We're gonna continue documenting and finishing. I mean, because we've got to build. In order to make it replicable, we got to document a lot, develop some of the techniques further, maybe do some redesign, see what we found out.
Recording everything too.
Yes.
Rewatch it like football players or
Yes.
anybody else.
We are studying the game
Yeah, exactly.
of abundance creation.
Yeah.
I love it. Our game is not the NFL. It's
We're
what is
better.
it? It's something else.
Yeah, we're better.
So, I have a question. How are we doing on the progression of the build? Like, what are
The progress of the build is good, I think. With so few people, we've got most of the structure done. Like structural modules are pretty much done. So the next step is getting that we got to put the plumbing into the foundation, and then as soon as we put the plumbing in the foundation, we're moving that foundation and putting all the modules together. So we're doing pretty well, and then we start finishing the inside.
Can I ask?
Yeah.
Alexa, was he here for the 3D printer thing? Is that how did you guys get together, and how is it that you're working on the 3D printer? If you don't mind me asking, I'm just curious.
Yeah, of course. I can answer it for that one. I actually kind of, it was like 5 years ago, I stumbled across Marcin's little TED Talk. You guys have probably seen the original one where he's talked about the tractor braking and the general gist of things. And it intrigued me. And then I waited a few years and found it again in like 2023-ish or so. And I was like, you know what? I love what's going on. I want to help. So I kind of just emailed him and said, hey, I'm planning on building a printer and I want to run a workshop and I want to do all this cool stuff. And he's like, pump the brakes there, Chief. It's going to be a lot more work than you think. And it was. But I decided to just take the extra time I had, a little free time here, a little free time there, and just flunk out documentation, take some pictures of what I built, design stuff up in FreeCAD, read over the wiki. God, I spent countless hours just poring over recent changes, looking through all the different core pages on the wiki that have a lot of that kind of theory of everything. And yeah, then I just kept on pestering him, sending him emails, letting him know what I'm up to, and letting all my changes just be released to the public for free, so that hopefully, if anyone else will benefit from the kind of fun work I got to get up to, then great. So yeah, I pretty much have just been for the past couple of years trying to poke at that same mission. My goal, my dream, would be to have a machine I feel is robust enough that you could, reliably compete with current, existing market competitors, but more on an open platform. There are a few other even existing open 3D printer platforms that are have their own aims, but I feel like this one's kind of the only one I've found that lives in that little intersection of appropriate technology and all the other lovely things that OSE gets up to. So I think we kind of just had a very similar overlapping set of goals, and I just wanted to kind of throw my extra effort at it. So that's what I've been doing.
That's awesome. Yeah,
And I think the rebar frame 3D printer is going to get major application. I mean, you have seen nothing yet, so there's good stuff coming.
A friend of mine, and that's the guy I was living with when I was in Nashville. His name is Alex as well, Alex Nardone. He makes good money. He just bought a really expensive, fancy 3D printer, and it was like he paid a lot of extra for it because I think it was a 2-foot box maybe or something, And anyway, it's pretty cool, man. I appreciate your effort and participation.
Oh, thank you. Yeah, and as far as the printer itself is concerned, the current bill of materials cost is only about $1,000. for the one that Marcin pulled up to show you guys on the screen there. And if we're going to go to the estimate that we talked about earlier, where the MVP for a large bank of printers would be, about $2,000 a piece. For $2,000 a piece, I'm going to be able to add improvements like closed loop servo motor control, so the printer will know exactly where its position is relative to where it's supposed to be. I'll be able to add all the frame modifications I want to make it super rigid, make it super strong, a lot more robust as you transport it. For $2,000, you might even be able to get away with a heated chamber up in there too, because the version 23.05, which is also documented on the wiki, has my kind of inklings of an idea of what would be close to a 2 foot by 2 foot bed printer with an included heated chamber and the D3D has a bed that lifts and the gantry, that's why gantry stays at the top, so that you can accommodate a big fully enclosed heated chamber for the printer, which is something you really don't see on anything but like $50,000 plus industrial machines at this point, because not too many consumers have the need to work on advanced engineering materials yet. Especially because they're expensive and those kinds of things. But as we degenerate through our tool chain, as we make things cheaper, as life gets easier because everything's getting open sourced, we're going to see a lot more impact from this kind of work. Mm-hmm. But I think open source about 15 years lagging behind open source software. And at this point, open source software rules the internet. That runs every server out there. It runs everything basically that thinks and is made of rock. So I think this is going to be kind of the next phase of the open Creative Commons sharing of everything. So that's why I wanted to help. That's why I wanted to contribute, because we can make a real impact on actual tangible issues for people all over the place just by putting some thought into things, writing it down very well, and sharing it far and wide.
Yep. Yeah, man. And I thought from your presentation the other day, just going over numbers and stuff, that the 3D producing our own 3D filament out of waste plastic is a huge revenue bucket. That's incredible. Like the ROI just on that, turning trash into gold. Basically.
Yeah. I mean, you're taking trash into gold. Yep. Turning trash into gold.
That's pretty awesome, but we need machines like this to make it valuable,
Yes, and you need the development to make it happen,
Right.
Mm-hmm. Quick question on the plastic stuff. You talked about 3D printing plastic stuff. What about, I don't know what you call them, but the mold plastic and also the bubble plastic forming? Have you ever seen those?
Vacuum.
The vacuum thing?
Yeah. What about it?
It looks like a balloon, basically, but then it's actually stretched plastic. Then it sucks it down onto a mold, and then instantly cools. That's one thing, and then there's just basic mold plastic where they make kayaks.
Holding the vacuum forming, I think you're talking about.
Yeah, that one. So I don't know if you thought of those as like.
No, I didn't think of much of vacuum forming at this time.
What about the other one? It was they put like plastic filament stuff in. I've seen them make kayaks out of it, where they have a huge form, a mold, and then they fill it with plastic.
Okay, so let's talk about that one. That's exactly what we're trying not to do.
Oh, gotcha. Okay.
Because you need a huge mold like that costs many thousands of dollars.
Yeah. And it only makes kayaks.
It makes that. A 3D printer does that and a million things, so that your return on investment is a million times higher.
Okay, that's good to know.
Just to clear up that discussion,
Yeah. Well, that's why I'm here.
Yeah. No, it's like, and that's the thing why I'm saying precious plastic. I mean, they're not getting that part. They do injection molding too. Cool, but 3D printing does anything that injection molding can do. In fact, much more, because you cannot inject the kind of geometries that a 3D printer can do. Right. So 3D printing is way more.
Sorry to interrupt.
Yeah, way more flexible, way more flexible and powerful. So we're talking about generative tools that can do 1,000 things, right? That's what we talk about. Mm-hmm. Okay, but let's wrap it up here, because I'm going to dig some dirt tonight, I think, with my brand new skid steer. I'm going to have to dig some dirt, because we're going to have to flatten a place for your house.
He's got lights
just to put it down.
Don't be alarmed.
I mean, yeah. So thanks a lot, everybody. I think this was pretty cool. I think we got across some good ideas about future directions for anyone who wants to get involved in 3D printing. And Alexa, definitely wants you to contribute on the skid steer, which we're getting the RTK GPS, basically precision motion control by a heavyweight contributor. So that's happening, and we're going to build one at the end of December here. So contribute on the parts that are 3D printed, the 3D printed tracks. One more comment on the 3D printed tracks. You know how tank tracks have all those tiny little sections that are maybe like, this wide and long, thin. On a regular printer, you can think about, here's those track sections that look like that, and they've got metal pins between them. That's something we can print on small 3D, something we can print on 3D printers that are small, like a 12-inch bed 3D printer. So that kind of, think about that, Alexa, think about that for 3D printed tracks. They're now modular. Like if it breaks, you can completely repair it and recycle it, and it's easier to put on, because one of the big pain points about the heavy-duty industrial tracks are the difficulty with which you take them on and off. They're very hard to take off. I mean, the people who do that cuss at that regularly. But this would be a great contribution, something that's lifetime design, recyclable, and open source, a fraction of the cost. So major cost savings. Maybe we can get that for the skid steer at this time. We'll see.
Oh, yeah.
Okay, victory. So yeah, thanks a lot, everybody, and we'll see you again tomorrow, 6 p.m. Take care.
Good
All
night.
right. Have a good night.
Bye-bye.
Bye, everybody.
Bye-bye.
Good night.
Bye.
That's cool, man.
Yeah, no, this is